Okay, so we are all set. It's my pleasure to introduce Amar Henni from the Federal University of Santa Catarina in today's edition of the Brazilian Algebraic Geometry Seminar. And he'll talk about fixed instanton sheaves on P3. Amar, please.
Okay, thank you, Marcus. Thank you for the invitation. So I'll be talking about this fixed instanton sheaves on P3. This is not a complete description, but kind of project. So, so my talk, I will introduce especially in the case of framed instanton sheaves. So I will talk about these framed ones. Then see what the toric action, how it lived to the moduli space of instanton sheaves, and how we can use it to get some information about this fixed locus in the moduli space. And then I will present for you some relation with stable pairs of Pandari-Pandey and Thomas, and at the end, relation with multiple structures and sheaves on multiple structures. Okay, so an instanton sheaf on P3 is a torsion-free coherent sheaf E with the first class Chern class 0 and satisfying the following cohomological conditions. So actually, instanton bundles originated in quantum field theory. The first article which cite them is due to, the first solution is due to Belavin, Polyakov, Schwarz, and Yupkin, where they're studying the classical solution to the equation of motion of some field theories. Then they were built as self-dual connections of principal bundles. On P3, they come as Atiyah-Ward transform of these connections on S4, and they are important in both theoretical physics and in mathematics. Since we are here confined, I will say that they are very important in the study of confinement of quarks and tunneling between different vacua. But more importantly, they will transport it to the realm of mathematics and algebraic geometry after classifying this solution, especially on S4, by the famous paper of Atiyah, Drinfeld, Hitchen, and Manin about the construction for almost all classical Lie groups, and this was built upon on the work of Horrocks and Barth and Hulek. Okay, so the torsion-free version. So this is about bundles. Then the torsion-free versions appear to by introducing degenerations where one want to compactify a la Uhlenbeck, the space of moduli space of these connections. Okay, on surfaces, it was they were widely studied, and they have many relations with the Nakajima quiver varieties representation theory, and also with the Huybrechts and Len framed sheaves and framed pairs, etc. On the other hand, there have been many generalizations in the last decades, usually, especially in the case of Fano threefolds, basically by firstly by Kuznetsov and Daniele Faenzi, and more recently for wider generalization by Malaspina and many of his co-authors in many papers. Okay, and in this picture there are relations with the ACM bundles and Ehrlich bundles, especially. Okay, so we will stick to the case of P3. Okay, and so the charge of the instanton is in the integer appearing in the second Chern class, and also appearing as minus the Euler characteristic of E tensor by -1. And we will say that an instanton sheaf is trivial splitting type if there exists a line such that the restriction on E is trivial. This is for even, I mean, I'm talking here for rank 2 or also higher rank. In rank 2, some of these will condition will reduce to simpler form. And I will say that particular choice of this trivialization will be called the framing. So the pair E phi is called the framed instanton sheaf. Okay. So using Beilinson spectral sequence and many other techniques, one can have these instanton sheaves as the cohomology of complexes, which are called monads. They are complexes of 3 vector bundles. On P3, they are of this form. V has V and W, they are vector spaces. V is of dimension the charge of the instanton. It's actually the dimension of this space here. And W is has dimension the rank of E. So if we stick to the case of rank 2, then the dimension of W will be equals to 2. Okay. So if we choose coordinates and let the framing line be Z0 given by this equation, Z0, Z1 equals to 0, then after some reduction of all the symmetries, many of the symmetries of the monad, we can write the maps alpha and beta in the complex in the monad as this form, where A0, A1, B0, B1 are just endomorphisms of V, I0, I1 are homomorphisms from W to V, and J0 to G1 are homomorphisms from V to W. So here we can see that this is closely related with the representation of quiver with 2 vertices. And the relations are given by these equations. And these equations are actually equivalent to the fact that beta composed with alpha is 0. So this is the complex condition on the monad. Okay, there is still some group action. Okay, so given by conjugation of the matrices A's, AI's, and BI's. And then there are multiplication by the right or by the left with the G and G minus 1 in the case of I and J. Okay, so one can consider the space given by all this ADHM data satisfying the equation 2 and with some stability. Here there are many stabilities that one can talk about. In this case, there are global stabilities that tells us when the complex is a monad, or maybe it can be also a perverse sheaf, for instance. But it's also good to characterize when the cohomology of this monad is actually locally free, torsion free, or reflexive. Okay, so at some point I will use this stability, but I will not talk a lot about them. So just to keep in mind these stability conditions. So the toric action that we will consider is the usual one on P3, this standard one. And applying this to the monad, and by the choice of the coordinate we have, we can lift the action to the space of ADHM data. And this is given by these transformations, so multiplying by T1, T2, T1 minus 1, T2, etc. These matrices. Okay, so in a way that the equations that are satisfied and the stability conditions are preserved. Okay. So what we can get from this toric action on the ADHM data is the following. So if the class of a datum in the quotient space is invariant by this toric action, if then there exists actually it is the action of the torus will give us another member which is in the orbit of G. Okay. And this is equivalent to say that there exists this morphism from the torus to G, such that when you transform these matrices, they are transformed also by G. Okay, so what we can prove from this is that if X is fixed by the torus, then J0 and J1 are 0. Okay, so they don't appear. And moreover, this X is what is called globally weak costable. So what this stability condition will mean is that it cannot be locally free. Okay, so the cohomology of the monad will not be locally free. And this is similar to the case of the action, the toric action on the on P2, for instance, if we consider like the Hilbert scheme, there is a proof of Nakajima of that the matrix G, the similar matrix J, is 0. And actually, the proof is kind of variation of the proof of Nakajima. Okay, so we are interested in the following consequences. So a T-fixed framed rank 2 instanton of charge C will be strictly torsion-free if the charge is positive, or is the trivial bundle if C equals to 0. Here I remind you that maybe I forget to tell you, but the trivial sheaf I'm considering as also an instanton bundle. Okay, and the second consequence is the following: is that the singularity set of this the fixed torsion rank 2 torsion free sheaf is purely one-dimensional, so it's supported on a curve, and moreover the double dual of this guy is the trivial sheaf, and the singularity locus is topologically supported on one rational line. Actually, it's a line given by Z2, Z3, which is the line, if you look at the polytop of P3 as a toric variety, then this line is the only torically invariant line that doesn't intersect the framing line. Okay? And moreover, the matrices that we are considering in the ADSM data are actually nilpotent. So this phenomenon is similar to the case also, this happened on surfaces where the invariant T-invariant part are given, for instance, if you consider framed instantons, are given by the direct sum of ideal sheaves, which are supported at the origin. So this is similar case, but here it's a little bit more pathological because there are this multiple structure that we will see one have to consider on these lines. Okay, so I remarked that the purity of the singularity set was also proved by Marcus Jardin and Michael Gargate in general. Here, my proof was set in the framework of T-fixed instantons, and similar behavior also were proved by me in the case of the blow-up of P3 using some slight generalization of Kasnati, Koskun, Genk, and Malaspina's definition of instanton bundles there. Okay, so the proof is based basically is based on the fact that E is reflexive, rank 2, and C3 equals to 0. So by a theorem of due to Hartshorne, it should be locally free. And this contradicts the fact that for our T fixed instantons, we don't have locally free ones. So the singularity set has to be pure, one-dimensional, because it doesn't intersect the framing line. Okay, and then purity is showed by showing that the quotient sheaf of the double dual is supported, is pure. So we know that it's supported in codimension 2. So these X sheaves are 0, and it suffices to show that X3 have codimension at least 4, since we are on 3-fold, so it has to be 0. And this is done by considering local to global spectral sequence and applying it to some analysis of the sequences coming from the monad, like display of the monad. Okay. And finally, to prove that the double dual is trivial, let us just remarking that the double dual is reflexive always, but then one have to prove that C3 equals to 0 so that we can apply Hartshorne theorem. And in this case, we only have the trivial as fixed instanton bundle. It's the only locally free one. Okay. So these are the first results we get. So before telling you more about the relation with these multiple structures, let me just say that we can prove in general that the moduli space of framed instanton sheaves of any charge, positive charge, it has the topological Euler characteristic is 0. And moreover, in the case C equals to 1, this is given by the Poincaré polynomial is given by this formula. So this is based on the fact that this moduli space is an SL2C bundle over the moduli space of all instantons. The surjective map, the projection is given by forgetting the framing. And in fact, if we are in differential topology, we can use the formula for the Poincaré polynomial. But since we are in the Zariski topology, this is not always possible. But we can always do this in the étale topology. Moreover, luckily, the group SL2C is special in the sense of Grothendieck and Serre. So this means that every locally isotrivial fibration is locally trivial in the Zariski topology, and hence we can use this product formula. And this gives the result because SL2C, we know it's Poincaré polynomial, and we can compute the Euler characteristic. Okay, so in the case of charge 1, we use the fact that the instanton moduli space is P5. This was proved by Jardim, Markuchevich, and Tikhomirov. Okay. So now let me tell you about stable pairs. So these are introduced by Pandaripandi and Thomas as generalizations of coherent systems studied by Le Potier and many other authors. So we fix a polynomial with positive leading coefficient. This is the stability parameter. And therefore, n integer and beta a cycle in H2 P3Z. So the definition here, I'm writing many things in terms of P3, but they hold for 3-folds, smooth 3-folds. And we consider pairs, so a pure sheaf on the one-dimensional curve. with this Hilbert polynomial and the section of this sheaf. Okay, so in the Hilbert polynomial, I'm writing beta, but yeah, it should be the integral with respect to the chosen polarization. Okay, so the pair QS is called Q semi-stable if for any subsheaf this inequality of the Hilbert polynomials hold. Here RT and RQ are the actually the leading coefficient in the Hilbert polynomial, and they called rank. And moreover, for any subsheaf through which the section has factors, then we should have this inequality here, as usual for large enough M. So this depends on Q, but then we can say that a pair is stable in the large limit, large Q limit. So when the coefficients of Q are very large, then in this case we drop the subscript, and these are given by a moduli space which was studied, and it has very good properties as perfect obstruction and etc., good deformation theory, etc. Okay, so there is also this characterization of these pairs. So a pair is stable in the large limit if and only if Q has pure dimension 1 and the co-kernel of the section has dimension 0. Okay, and in our case, we will call a stable zero instanton pair if rank 0, sorry, it's not 0, but rank 0 instanton pair, if it is stable and then Q is an instanton, a rank 0 instanton sheaf, so it satisfies these two cohomological conditions. Okay, so how do we obtain, in our case, these stable pairs? So we take the quotient of our fixed instanton, and we get this quotient. In this column, this is just the split sequence, and combining these two maps, we get a section. And the image of this section will be the structural sheaf of a curve. And then, okay, we know that this curve is supported on this line that I was telling you about before. Okay, and one proves actually that the co-kernel of this section is supported on points. So actually, in our case, this is an instanton, rank 0 instanton sheaf. It's supported on a curve, and this pair is stable, and moreover, from the fact that the co-kernel of S is supported on points, we get E as the extension of an ideal sheaf of subscheme of pure dimension 1 and the ideal of zero-dimensional subscheme. Okay. So, okay, so this will lead us, we want to characterize this instanton rank 0 instanton sheaf on this multiple curve. So we know, we want to know more about it, more if it comes in families or not, because we want to have a description of the moduli space in terms of localization to this fixed instantons, but unfortunately, this is in this case it's more complicated. The behavior of these multiple structures is more complicated than the behavior of multiple structures on points, like in surfaces. So the motivation of studying these things was first to study the relationship between, having a representation of the Heisenberg algebra also in this case. Because these rank 2 instantons, they come from the one on S4, so they are like the related to the one studied on surfaces by this by the correspondence Hitchin-Kobayashi correspondence like. Okay, so multiple structures were studied by many authors. Banik and Foster were the first to study this systematically, and also by Watney, studying monomial multiple structures, and many different features on sheaves on multiple structures were also studied by Drezé, especially in this paper Faisceau cohérent sur les courbes multiples. And most of this material that I will present here comes from the papers of these authors I was mentioning. Okay, so also I would like to say that in many cases I'm writing P1, but the results are general for smooth curves as simple structure. Okay, so we consider the embedding of I in P3, of P1 in P3 in this case, given by the saturated ideal, and we consider the infinitesimal neighborhood. Okay, and for Y, a multiple Cohen-Macaulay structure with reduced structure exactly the X. We have the following filtration. Okay, so this filtration is given by intersecting the multiple structure with the ith infinitesimal neighborhood. Okay, and each term in this filtration will be a Cohen-Macaulay. This is true for curves, but it's not true in higher dimension. If I consider multiple structure on higher dimensional, let's say linear spaces. Okay, so with this, one has these two exact sequences associated to the restriction of the ith plus 1 structure to the ith structure. And in this case, we will have all the kernels as locally free OX sheaves. So in this case, P1, we have just locally free bundles on P1, which are the sum of line bundles. Okay. So some results that we will be using is, in this case of monomial ideals, we have a bijection between Cohen-Macaulay monomial ideals and in two variables and Young diagrams. And in this bijection, the number of boxes is the multiplicity of the scheme. Okay. And so you take your favorite monomial ideal. In this case, I will take J given by Z2 cubed, Z2 squared, Z3 cubed, and Z3 cubed. And this will correspond to this diagram here. The number of boxes is 8, so the multiplicity is 8. If I consider just the simple curve, then it's associated to the box 1. Okay. I will define inner boxes and outer boxes. So an inner box is a box such that the box it's not in the diagram, and the box below it and in its left are in the diagram. and an outer box is for which the box on the left and below it are not in the diagram, but it touches the left angle box in the diagram. So in this example here, we have the red box is an inner box, and the outer box is given by this green one. Okay, so sorry. So this will be useful actually to describe the ideals by means of resolutions. Okay, and we have this theorem that every Cohen-Macaulay monomial ideal will be given by this resolution. Okay, and N1I are the weights of the inner boxes, and N2J are the weights of the outer boxes. So in particular, the CZs will correspond to outer boxes. Okay, so with these results, we can compute many things about the curve. In our case, supporting the rank 0 instanton pairs. So for the associated C multiple structure, on which Q is a sheaf, we have, if it's given by a Young diagram given by this partition, then we have the polynomial, Hilbert polynomial given by this formula. So the constant term in the Hilbert polynomial depends on the partition. And then the length of the sheaf, which is the cokernel of this section, will be also dependent on the partition in this way. Okay, so I have many invariants of the supporting curves that are computed. Okay, and for us, this means that one can view the part, the invariant locus with respect to the toric action on P3 in the moduli space of framed instanton sheaves as a union of indexed by the partitions of this generating function. This is the least number because actually we don't know in general if these pairs, they come in families, if they are rigid. There is really a difficult problem of looking at their deformation. And for the moment, we don't know. We don't have many informations about them. Even like the tangent space to compute the weights, some weights with respect to their tangent space. Okay, so in the following examples, I will show you that in some cases there are more fixed points than this number here. Okay, so before this, I will just tell you about primitive multiple structures. So these are multiple structures such that for every x in the simple structure, there is a surface in P3 that is smooth at x and containing a neighborhood of x in y in the multiple structure. So in particular, these are locally complete intersections. Okay, and in this case, the line bundle given by the restriction of the double structure to the simple one, this sheaf is a line bundle, and for every restriction from I plus 1 to the ith multiple structure, this is just the tensor product, the tensor power. Okay, so here more definition. So we call the first canonical filtration of a sheaf on this multiple structure the following filtration given by these members, where you take F, you restrict it to the simple structure, and then you take the kernel, which is F2. Then you restrict F2 to the simple structure, and you take its kernel, which is F3, and you complete this this procedure, and you get all the terms. Okay, so this is there is another filtration called the second canonical filtration, but I'm not telling you about because I will not use it. Okay, so this allows us to define a graded object, which is an OX model. So this is a sheaf on the simple structure. Okay, and this is used, so first some properties. Every sheaf in this filtration is supported on the ith, the restriction to the ith multiple structure. If you have n, then you restrict and to I less than c. And the canonical filtration of this guy is just the truncation of the filtration. Okay, and the other important property is that it is compatible with morphism of sheaves. So filtrations go to filtrations, and so we have morphism from graded object to the other one. Okay, this is used actually to define a generalized rank and generalized degree, because usually these are not defined, or in many cases these are not additive on exact sequences when we consider multiple structures. So these are not anymore multiple additive, and we to study sheaves on these multiple structures, sometimes we have to know about their invariants, and we know that if these invariants are additive on exact sequences, this is better situation. Okay, so with these two invariants, one can have this generalized formula, Riemann-Roch formula in this case, proved by Dreise. Okay. So I remind you that in our case of the rank 0 instanton sheaf, this is given by sequence of, we have a multiple structure here, Q, and then something supported on points. Here I'm writing Z, but it's the structure sheaf of Z. Okay, and if the charge is 1, then the multiplicity here is 1. So we have just a line. Okay, and then we can prove that. There is only this possibility here. So in this case, Q is OL01. And the corollary is that we have just one fixed point under the lifted toric action. Actually, one have to look to projection from O2 to this sheaf, and then prove that this is only one sheaf in the modular space. I mean, the kernel of this map. Okay, so in this case, we have the same number as the partitions. So because we have just one box. For charge 2, we have two diagrams that we can consider. And the ideal of double structure is given by this resolution. Okay, so we can compute its Hilbert polynomial, and we can compute the length of the cokernel of the section S, which is in this case 3. Actually, in this case, both diagrams correspond to primitive multiple structures, and the canonic, this exact sequence here, the restriction to from the double to the simple structure is the canonical filtration of the sheaf, the structure sheaf of the curve. And then we have the graded object and the rank, generalized rank and degree. We can do the same for our rank 0 instanton sheaf, okay? And then because of compatibility of this morphism with the restriction and the filtration, the first canonical filtration, we have this structural sequence for our sheaf restricted to the simple line, and we get these sheaves as kernel. One can prove that Q2 in the filtration of Q is given by OL minus 1, and so this will have generalized rank 2 and generalized degree 2. This is the charge of the instanton 2 in this case. Okay, and one can prove that the restriction to the line is given by OL1 plus some torsion sheaf of length 1. So, so here I'm using this filtration to give some more characterization of our rank 0 instanton sheaves. There, you can view them as S equivalents if there are families. Okay, it's not that precise, but something like this. Okay, and so this is based on the fact that on the double line, the generalized rank 2 can be only line bundles on the double structure, vector bundles of rank 2 on L0, or strictly torsion free. And it turns out that in this case, it's strictly torsion free. So there are simple sheaves on double structures, also called ribbons sometimes. Their the moduli spaces were studied, but still very complicated. And in cases where these sheaves are called quasi-locally free, so that their graded sheaf is composed of only locally free components, there are some characterization of their deformation theory, but for more general as this one, still we don't know almost nothing. Okay, so of course one can go back to the moduli space of the fixed instantons, and one can prove that there are at least 2 irreducible components because of these 2 diagrams. We're not sure because it might be that these the families of these sheaves also comes in different components. Okay, so I don't have a clue. For now, how to compute such components, or maybe to see that these are irreducible. So we have exactly 2. Okay. So I will skip the proof here. And in the case of charge 3, we have 2 primitive cases given by these 2 Young diagrams, and then we have a non-primitive case. So if I consider my favorite sheaf on this, my multiple structure, and impose the instantonic condition. So on the terms of the filtrations and their quotients, we can have these conditions, and we use them actually to prove that in this case, for the primitive monomials, so this one and this one, for each one of them, we have 2 cases. We have this first filtration in which all the terms are locally free and the graded is locally free. So in this case, our sheaf is quasi-locally free. and the other one is wilder, and it can be it is with restriction to the simple structure with torsion sheaf of length 1. Okay, so for higher charges, like starting with 3, the things get complicated, but still we have some control here, because here we don't have a canonical filtration, okay, but both filtration that we can consider, they are equivalent in some sense, so it's not very complicated situation. If we consider more complicated partition and Young diagrams, we have many more filtration, and we don't know if the results will be filtration independent or not. Okay, so in this case, it is filtration independent. And for this guy, we can have 3 other cases. So we have one sheaf which restrict to OL1 plus a torsion sheaf of length 3, and with the filtration given by these exact sequences, or the restriction to this simple line is given by OL2 plus a torsion of length 1, or another case where this is quasi-locally free. So all the terms of the graded object are locally free on the curve, on the simple curve. Okay, so in this case we have seen that we have 7 cases, and it's much more than the number of Young diagrams that that are the number of partitions of charge 3 instantons. Okay, so in general, we can maybe say something about only the primitive case. So these are the ideals in our case given by Z2 and Z3 to the power C, and they have this kind of resolution. We can have Hilbert polynomials, and the length of the cokernel of the section given by C plus 1 over 2. And the filtration is given just by taking one box of the diagram at each time. Okay, so here we can compute the graded object for the structural sheaf of the support curve, and its generalized degree and rank. Okay, and okay. So let me just tell you this final remark. So in the case of charge 1 and 2, we know that the moduli space is irreducible. So all these configurations, actually they are in the closure. This should be in the closure of the locally free open set. But in general, this is a hard problem. We don't know if the sheaves corresponding to the fixed locus are smoothable. So we believe that it's true, but it's a conjecture that it's more than like a wishful thinking that the fixed component will intersect the closure of the locally free component in the moduli space of framed instanton sheaves. Okay, so I will close with another conjecture. So that the fixed instanton pairs in the moduli space as pairs are smooth. So this is conjectured by Pandaripandi and Thomas in the case of Calabi-Yau. In our case, this is we computed for charge 1 actually and these are smooth, and we think they should be also smooth, but I don't know if it's also a kind of project. So so it's still like a dream. Okay. So I will stop here. Thank you for your attention. And okay, thank you.
Thank you, Amar. Are there any questions?
Yeah, I have two.
So please go ahead.
Yeah. First of all, Amar, I'd like to say that your lemma, when you compute, when you have a generating function for the number of reducible components, was very nice. I also have a dream of finding something for that for other components, but very nice job, very nice. My question indeed is that you know if these T fixed components are indeed reducible components of the whole moduli space?
No, we don't know. We don't know this. I mean, first, we don't know if they come in components. So they might be, or in some cases, they might be isolated points. So actually, I don't have a clue how to prove this. So this is one of the difficulties because we have to study the formation of these sheaves. And I think in your work with about the irreducible components, you know that this is very hard to link some instantons in one component to another one or vice versa. This deformation problem is very hard. Maybe we can tackle some cases with low charge in, I don't know, in the future, but in general, I think it's hard. Yeah, I don't know.
You say that you have zero-dimensional components even for higher charges.
Sorry?
Even for higher charges, you can.
I mean,
you can have.
I don't know. Since I cannot find families of them, I cannot state that they come in families or not.
Okay. Okay. And well, this almost answers my other question. That was the main problem to prove that the reducible components that you found for charge 1 and 2 is that you cannot know how to deform these guys.
Yeah.
You don't know how to. Okay. Okay. Thank you. Thank you.
In the case of charge 1, it is 1. But in the case of charge 2, for instance, I don't know.
Okay. More questions? So I have a question of my own. In the beginning of your presentation, Amar, you said that from a fixed instanton, you get that the associated matrices, the matrices associated to a fixed instanton are nilpotent.
Oh, yeah.
So you have some.
Okay.
So the fixed instantons will give you nilpotent matrices A and B, and the J0 and the J1 are 0.
Yeah. Okay. So
does the converse hold? So if you have a solution of the ADHM equations for which the matrices A and B are 0 and the J is 0, then this is a fixed instanton.
I don't know, but I expect maybe not.
Maybe not.
Maybe not, because you can have, for instance, some you can have a multiple structure on this line, but which is not monomial. So it cannot be fixed because the monomial ones are the ones fixed by this torus action.
Okay.
So I don't know, maybe not in general.
Okay. More questions, anyone? So let us thank Amar again.
Thank you.